Hello, my name is Chandler Dorsey. I'm attending the Georgia Tech Challenge program for 2017, and today I'll be talking about how to find the volume of figures using calculus in the definite integral. So some basic things to start off with. You can find the area under a curve using the definite integral by taking the antiderivative of the function and then plugging in the bounds. So for here the bounds are 2 to 0, and you'll just plug in 2 to the antiderivative function and 0, subtract it from 0 into the antiderivative function, and you get 8 over 3. So the first problem that we have to work is the base of a solid is the region in the first quadrant bounded by the line x plus 2y equals 4 in the coordinate axes. What is the volume of the solid formed if every cross-section perpendicular to the y-axis is a semicircle? So we'll set this up first by just drawing it out. They said that the line equation was x plus 2y equals 4. So we can figure out what type of line it is just by plugging in points. You plug in 0 for x and you'll get 2. And then we know that if you plug in 4 for x, y will equal 0. So that gives you an idea of what you're working with. Now, it said that the cross sections were perpendicular to the y-axis. So we're actually going to put this in terms of change in y. And because we're working with change in y, we want our equation in terms of x equals. So now that is the equation of the line. So how we go from here is we'll take a little sliver out like this with the undefined change in y. And it's a semicircle, so it's going to look kind of like this. Right? So, to find that area of the little cut in the function, you do 1/2 pi times the radius squared, because it's a semicircle. And then this whole thing is the diameter, right? And if we label our point, it's x f of x, right? So this whole diameter is f of x, therefore the radius is going to be f of x over 2, right? This is f of x, so when we write it all out, this is what it looks like. And we do some reformatting, some simplifications. And we get that. Right, so from here we'll simplify some more. And now we have the volume of that little section. So now the next step is to get the volume all across the bounds from 0 to 2. So what we'll do for that is we'll take the antiderivative or the definite integral. And from there, if you follow the fundamental theorem of calculus to solve that setup, then you'll come out with the area of the volume of this little semicircle semicircle figure. Right, so something else you may be faced with when trying to find the volume is when you have a function rotated over an axis. So we'll use a simple function again, just x squared, and we'll rotate it over the x-axis. So from here we do the same, kind of the same thing, just take a little sliver out, label a point, and we want to know what that small little cylinder is, right? We know that part's changing x, so we know the area is going to be pi times the radius squared times changing x. And then already looking at it, we can tell that that radius is equal to f of x. So it'll be x squared times changing x, right? So we know the volume of that little section. Now we need it across the whole bounds, and we'll set the bounds at 2. So from here you just take the antiderivative. And there you have it. So I hope you, that was a good refresher. I hope you learned something, and thanks for watching.